Right. So it's my pleasure to welcome Paul. He's going to talk today about the combinatorics and conjectural geometry of Steinberg quotients. So,
All right, thanks, Scott. Thank you. I want to thank the organizers. Yep, okay, it works. For this invitation. I think Tekken had invited me about 3 or 4 semesters in a row.
yeah.
He really wanted my family to come, and they didn't. I apologize for that. But yeah, good to be here. Great to be in this seminar. So if you were at Dan's birthday conference less than a year ago, I talked about something along these lines. And so some of this is going to be a repeat from things I said there. However, if you may or may not remember, I did not manage my allotted time super well at that talk. And so even if I give exactly the same talk, it'd be some new stuff, but there will be a wrinkle added at the end that I did not talk about at all there. Then it occurred to me, if I just completely changed the title and some notation, would anybody know it was not the exact same talk? I don't know that people would figure these things out. So I want to talk about these things called Steinberg quotients, which have to do with character formulas for modules. And I'm trying to promote them as something I think is important. So let me just give the quick setup and then give like the historical motivation. So we're dealing with reductive groups in characteristic P. So K is some algebraically closed field of prime characteristic. We're going to have a connected reductive group. So general linear group or special linear group are very good concrete examples to have in mind. And when you're doing characters, the idea is when you have a representation or a module for a group, then like the most basic kind of information you could ask is what's the dimension of the module? And that's essentially the same as like forgetting the G structure and thinking about restricting it to the trivial subgroup inside of G. So a slightly better thing that you could do is you can restrict to something like, in the case here, a maximal torus. And that has a more, sophisticated representation theory than the trivial group, but it's still very nice. Everything's a direct sum of one-dimensional representations, and you retain a lot of information by restricting G modules to T modules. Like in characteristic 0, a finite dimensional G module is completely determined by its restriction to T, if it's a reductive group. All right, so a couple of things that just to get out of the way, phi will be the root system for our group with respect to this torus. The weight lattice X, that parameterizes the simple T modules. Inside there are the set of dominant weights. These parameterize our simple G modules. The same set parameterizes in any characteristic for a given root datum for the connected reductive group. In characteristic P, we're interested in the set of P restricted dominant weights. So I'll try to indicate what that is, but roughly speaking, the coefficients have to be non-negative, but they have to be less than or equal to P minus 1. And then L lambda will denote the simple G module of highest weight lambda. Okay, so kind of some motivation behind this. So this was a paper by Jim Humphreys that appeared in 1971. And it was a very important paper where he worked out a lot of the block theory of a restricted Lie algebra for a Chevalley group. For me, it was a really important paper because when I was a graduate student, it was like the first sort of substantial paper about Lie theory that somebody pointed me to that I started reading. And I remember that, you read papers, you kind of read the beginning and the parts you need, and then the concluding remarks. And so at the very end of this paper, there's like the last paragraph in the paper. He says, finally, the problem of finding a Weyl character formula in characteristic P seems to be as open as ever. Does there, for example, exist any reasonable formula for dimension of M sub lambda comparable to Weyl's formula in characteristic 0? So just to kind of match things up, his M sub lambda would correspond to L of lambda in my notation. In his set here, capital lambda, that would be the P restricted weights. So he asked this question in 1971, and it is kind of, I had to kind of laugh here, and I'm guilty of this, but mathematicians were extremely precise in general, right? Like we give these mind-numbing definitions of things, the datum attached to something, and we get really precise. And then we throw around things like we're looking for something that's reasonable or nice enough or an elegant description. And of course, the question is like, to whom? So I would say that using any reasonable definition of reasonable, we still do not have something that does this. I don't think that in 2025 we have found a characteristic p-analog of Weyl's formula. Now, it may just be the case that it's impossible. Like, nothing reasonable can exist that will capture all the complexity. But in any event, I don't look at people nodding. When people agree that that seems reasonable, you can challenge me if not. But so this was 1971. I remember this comment. I wasn't really thinking about these things, but it was an interesting remark. And this has actually driven this has driven a large chunk of the theory in this area, trying to resolve this problem. And as a byproduct, like, beautiful mathematics has resulted. So in some sense, the stuff that's come out that has tried to chip away at this, you could say has value in its own right and for other things. But I will just make the comment, I still don't think we have anything like Weyl's dimension formula. Okay, so let's try to say a little bit more about what we do have. So here's more notation. So again, if you've seen these, you know what they are. And if you haven't, there's not enough time to absorb it. But for the record, so I can check some boxes here, rho is going to be the sum of the fundamental dominant weights. Our characters, we think of them as living in the group ring of this character group. So X is it's a free abelian group. And so its group ring is like Laurent polynomials and several variables as a ring. W is going to be the Weyl group, which acts on the weight lattice. And then, of course, we have the affine Weyl group. I actually meant to p-dilate this thing. Okay, so we'll have to p-dilate the action. You take the finite Weyl group, and then we allow translations by the roots. But we're actually in characteristic P going to want to take P translations by the roots. The dot action, which is often going to be what we use, this is where the Weyl group acts, typically in an action, like here's a picture where the blue lines intersect. That'd be the zero weight, the zero element in X. And so, your normal action, everything would be happening with you fix zero. The dot action moves the fixed point to negative rho. So by adding rho to a weight and then applying the action of W and then subtracting rho, we've shifted things. So that'll come up. And then the W invariance, the regular action of W acting on X, the W invariance of this group ring, this is where the characters of G modules live. So and this is going to be really important right now. So for every dominant weight lambda, we'll denote by S of lambda the orbit sum of lambda in here, which will be a W invariant element. So the idea is, if I think of my basis elements in this group algebra as being like E of a weight, something in the weight lattice, then what I'm going to do is for lambda dominant, I'm just going to take all of its Weyl group orbits. I'm going to sum those up, and that's a W invariant element, the opposite element in here. And every character of a G module has to be a non-negative sum of these things right here. So those are going to pop up in our work. I should have said at the outset, stop me if you have any questions along the way. So I'm going to look at people. So this is the worst part of a Lie theory talk, is you got to hit the notation, and there's just no getting around it. Okay. So let's stare again at Weyl's formula and think about what makes this nice. So if I have a dominant weight, then so what we're going to look at is the character of the simple module for the complex reductive group of highest weight lambda. That character is going to be given by this, what we'll denote as chi of lambda. And the one expression that you might see for the formula, Weyl's formula, is this thing right here. So what are we staring at? Well, a second ago, we defined these orbit sums. And here what's happening is, if lambda is dominant, then I shove it, like in this picture, let's say this is the dominant region. By adding rho to it, I'm shoving it properly into the dominant region. And so when I act by the Weyl group, the orbit's going to be equal to the size of the Weyl group. There'll be no stabilizer. So you take the orbit sum of this thing, but it's not quite the orbit sum, it's a sign sum. Okay, so you have, the W is a Coxeter group, and so you're looking at some kind of a sign sum. So this is not an orbit sum, it's got sign changes. And then this thing down here is not either. And so the first thing that's not necessarily obvious is that, where does this thing even live? Well, a priori, it just lives in the quotient ring of Z of X, right? But the statement is that actually the denominator does divide the numerator, and what's left is something in here, and you get these orbit sums that give you the character for the module. Okay, so that's Weyl's character formula. Let's just quickly look at it in practice. So if you're taking like SL2, which is the absolute easiest situation you can get, then the weight lattice identifies with the integer. So we'll take, there's only one fundamental dominant weight. So rho is that weight. So you have Z rho, and we'll just write M for M times rho as a weight. And then our dominant weights would just be the non-negative integers. And so what does Weyl's formula look like here? Well, the Weyl group's only, it's just a symmetric group on two elements. The non-trivial element, just what it does to your weight lattice is just multiplies by -1. And so if I have the weight M, then if I add rho to M, that just makes it M plus 1. So I have the basis element for E of M plus 1 in the group algebra, minus, then when I flip that, I get E minus M plus 1, and I'm dividing by this denominator here. And this gives us the familiar fact that the character for the simple module of highest weight M is just all the weight spaces are one-dimensional. It goes from M down to -M, and you just drop by 2. And we see the orbit sums appearing, right? That's the orbit sum for M minus 2, and they appear going in like this. And every orbit sum contains two things except for the zero weights in its own thing. Maybe this would look more familiar if we just take the isomorphism that Z of X is just Laurent polynomials, and then maybe if you stared at it like this, you'd say, oh yeah, that looks like a familiar thing. But if I'm writing instead of E of whatever is T to the, then you can see Weyl's formula in action there. I don't know, it looks a little prettier to me seeing it like that. Okay, so that's Weyl's formula in action for SL2. Let's stop for questions. So, any questions on the mumbo jumbo or the examples? Okay. So for SL3, similar situation. Now the set of the weight lattice is Z cross Z. And again, I'm going to take dominant weights have non-negative entries. So if I take the dominant weight of weight 4, 4, then what's happening here is this represents the set of dominant weights, the places where the grid lines intersect, that's the points on the weight lattice. And so like, this would be one fundamental dominant weight, this would be another, rho would be the sum of those two. The numbers here are indicating the multiplicity of the occurrence of the weight in the module. So I take the simple complex module of highest weight 4, 4, then these are the weights that appear with this multiplicity. 4, 4 appears once, and then all of its Weyl conjugates, those are the ones that are circled. And then we sort of see this phenomenon happening that as you move in, as the orbits pinch in, the multiplicity increases. And it's not too hard to see why why it has to at least be monotonic. The question is, when does it actually make a jump in value? But it can't decrease as you go in. So that's what's going on for SL3. Okay, so what do we like about Weyl's formula? Well, the first thing is it packages the character into a very concise expression. You're staring at a fraction. And so in principle, all the information's right there. Now, can you extract the information? That's the challenge. But in principle, you say, okay, here's everything about this module, at least its character. The computation of the character is really only involving arithmetic and Zx. So X is a poset. The weight lattice is a poset. And so really all you're kind of using is you take these quotients, then when you go to do the division, you're going to use the partial order on X, the W action, sort of everything's happening right there in what you have to compute. And we know which weights appear. So in chi of lambda, I know which dominant weights appear. It's all the dominant weights that are less than or equal to lambda in the partial order. And the multiplicities are non-decreasing as we work our way in. And then, of course, Weyl's dimension formula. That is extremely computable. So these are some of the things that make Weyl's formula really attractive. Okay, so do we have something like this in characteristic P? So, so what was known in 1971? Well, as it pertains to the talk, I don't mean in general. We're not going to do a world history tour here. So when Humphreys was writing this, like what facts did they know about G modules then? and then how's it kind of progressed in the time since. So here's some things that were known, kind of written with modern notation. But the category of G modules in characteristic P is not semi-simple. That's the biggest problem of them all, is that you can take your simple things and glue them together in lots of ways and create all sorts of complicated modules. So in characteristic 0, the only indecomposable modules are the simples, but in characteristic P, they knew that there were a couple others. So there's what we call the induced or co-standard module, and nabla of lambda, and then there's the Weyl or the standard module, delta of lambda. And these can both be obtained from characteristic 0 by a base change. And they both, sometimes they're actually going to be isomorphic to the simple module of highest weight lambda in characteristic P. But in general, they're going to contain this thing as a composition factor uniquely. So either at the head or at the bottom, and the pointy side of the triangle tells you which one it is. So again, that's the most inspired notation, I think, in all of mathematics was whoever figured. Was it Ringel who did this? Or anyway, I just want to give an applause for that person. So you have these indecomposable modules, the simple modules inside of them in a canonical way. And what we know is that these indecomposables, they have the same character as the character of the simple module of highest weight lambda in characteristic 0. And this was known when Humphreys was writing that paper. And so like it was, already known that, well, whatever the character of this thing is, it's like bounded by the character of the complex module that way. And in particular, the dimension is less than or equal to the dimension given by Weyl's formula. Another tool that was known was the Frobenius morphism. So if I have a group in characteristic P, then I can, like for example, for the general linear group, you take a matrix and you raise each of the entries to the Pth power. That in characteristic P, that's a group homomorphism because of the freshman dream. And so that gives me an endomorphism from the group itself. If I have a module for G, M, I can twist it by that action. So we denote it as M upper 1. And from a character standpoint, twisting is extremely transparent. If I know the character of M, its twist is just like P dilate all the way. So in fact, the relationship between the two is the weights there are P times the weight here. Not the multiplicities, the actual weights that appear are P times the weights that appear in M. So that's an easy thing to understand. And then we had Steinberg's theorem, which is, if you have a dominant weight lambda, then, okay, I did a sort of a truncated p-adic decomposition. What you can do is you can take lambda, you can write it as a p-restricted dominant weight plus p times another dominant weight. And you can continue this process till you've written it just as restricted plus p times restricted plus p squared times restricted and so on. But the key point is that Steinberg's tensor product theorem says that L of lambda is isomorphic to a tensor product of L lambda 0 with L lambda 1 twisted once. And so as a consequence, all you need to know are the characters for the restricted dominant weights. So that's a reduction. I would argue that that also poses maybe a challenge, or it says that whatever formula you have has got to scale according to this thing. So you know that if you have a formula that's going to compute characters or dimensions of simple modules, it's got to account for, like if it's going to work for all weights, it's going to have to scale. If you cap it at the p-restricted region because of this reduction, then I don't know, it's a little bit awkward to cap something at the p-restricted region. So this is both a help, but it also says there's like a wrinkle in your formulas you've got to account for. All right. So, okay, so this is what was true at the time that Humphreys wrote his paper, and he said, we're looking for something like Weyl's formula. So why don't we have anything like it today? Well, shortly thereafter, in the 1970s, a more dominant perspective in characters emerged, which is the standard module approach. And so Janssen's written a very interesting survey called Character Formulae from Hermann Weyl to the Present. That was the present like 10, 15 years ago. So it's not the present anymore. There's a lot more that's happened since then. But it gives you a good story about how the search for character formulas evolved. And what happened was it became normal to try to take the character of a module you're interested in and write it in terms of something whose character was easier to write down. And the main example would be Verma modules, who are these infinite dimensional modules, but their characters are extremely easy to, like, in principle, to write down what's in them. And so that viewpoint sort of took over. And in the algebraic group setting, that perspective works well, because if I take this would be what we call the standard module in this setting. I take my delta lambda. It's an indecomposable G module with L lambda sitting at the head. All of the other composition factors, L mu, are strictly smaller in weight than lambda. And so there's a decomposition and a growth of D group that looks like this with some, mystery multiplicities here. You can invert that, and you can invert that decomposition, and you get that the character of L lambda can be given as a sum of Weyl characters. In the case that these are not equal, these first two, then necessarily some of these are going to have to be negative to pull stuff off. And you're going to have a alternating sum or something. So Lustig had the big conjecture that everybody expected would resolve this problem. That at least when P was big enough, like bigger than or equal to the Coxeter number was what the settled bound of expectation was, that these multiplicities here would be controlled by Kozan-Lustig polynomials. And I mean, this was so like, again, I was not maybe super active in the heyday of, but when this was, that time period when this was expected, because Geordie had already broken the conjecture around the time I was really getting interested in it. But you read a lot of math papers which will say, assuming Lustig's conjecture, et cetera, et cetera, et cetera, with the assumption that Lustig's conjecture holds, then we can prove X, Y, Z. Well, it turned out that his conjecture was correct for extremely large P, but in 2013, Geordie found it to be incorrect for surprisingly large P. You're going, what in the world? What's the difference? How big is extremely large? It's somewhere north of surprisingly large. I don't know. I mean, it's like, there's counterexamples in characteristics so big, it irreparably breaks the conjecture. Like, the bounds you're going to have to settle for are going to be too big in general relative to the data of G. But there is a bound for any group. There is a bound after which Lustig is right. So, from, again, depending on your perspective, Lustig was right or he was wrong. But ultimately, we needed something else. And so, yes. Up here you're talking about? Yeah, so first of all, this kind of a situation, we really, let's go ahead and say we have a restricted weight here, because that's right. Yeah, that's right, I stuffed that. So because we had that reduction, we can just think about restricted weights. There should be a stipulation here that we're just talking for.
There was a conjectural condition on P at first.
I think the initial condition was like P bigger than or equal to 2H minus 3 was Lustig's maybe guess. And then Kato showed that it could be made compatible with Steinberg's theorem. And so he lowered it to P being bigger than or equal to H. So the expected bound was like, so for the general linear group, the Coxeter number, so for GLN, the Coxeter number of the group is N. So, the expectation became, well, if the characteristic of the field's at least N, then Lustig's conjecture should be true for GLN. And and Geordie found like this amazing set of counterexamples where the counterexamples kept getting larger and larger relative to the rank of the group. And so, there was really no fixing it at that point. Sorry, let me start. Other comments, questions? I have dropped a few things in the interest of simplicity, but I'm glad Dan pointed that out. Okay. So the big kind of point that changed history here was Geordie's counterexamples. We just showed that, Lustig's conjecture will only work when the prime is very large in general. So where character formula sort of moved from there was to indecomposable tilting modules. And these things, I love them. I think about them a lot. Nate's with me in the back. We've bonded over those at some point, probably mathematically. But yeah, Dan, I really thank Dan for getting me thinking about tilting modules. And so, in fact, Dan and I are still thinking about tilting modules about 2 hours ago. But so we are interested in them with something to do with their projectivity, injectivity over the first Frobenius kernel of a group. Shortly after Geordie's counterexamples, Geordie and Simone Riche proposed a character formula for tilting modules. And so what is the tilting module, just very quickly? So for every dominant weight lambda, we had at least 3 indecomposable modules of highest weight lambda so far. We had the simple, we had the standard and the co-standard module. And now we have this new thing, the tilting module, and it's a module that can be filtered in a priori 2 different ways. It has a filtration with factors that are nablas and a filtration with factors that are deltas. And I've completely skipped over interesting X vanishing properties of these modules, which make the tilting modules extremely interesting. So somewhat out of necessity, I guess, they moved the character formula to this other set of modules, but it turns out I think this is a much richer thing to do because, so they gave a formula so since these tilting modules have filtrations with modules whose characters are given by Weyl characters, the character of a tilting module can be given as a sum of Weyl characters, and there's no more of this, all the coefficients would be non-negative now, because it's actually filtered by these things. So it'd be different than the simple module. They conjectured that the character would be given in terms of some kind of sums of Weyl characters, and there would be some kind of Kazan-Lustig-ish polynomials that control it, but these things are more complicated. To this day, still, I have this like very vague, I don't know how many talks I'm gonna have to give before I actually can give the definition, so please don't ask me to define it. Promote, maybe can define them in the next talk, but you're not going to. Okay. If you help a friend out, no, you don't. Anyway, but the problem is, I'll just take it off a comment Geordie's made. This conjecture, by the way, is a theorem now, proven sort of in stages, but is now true for all characteristics. So this is a fact. Unlike Lustig's conjecture, this is known to be true in all characteristics. And what's good is if you can compute the tilting characters, you actually get all the simple characters. Like there's a way you can go from one to the other. So it somehow is more information, or at least greater than or equal to information that you get in the simple module case. I think it's strictly more. But the trade-off is that the Kazan-Lustig polynomials are very complicated to compute. And again, I'll just say, like, I've heard Geordie remark on the magnitude difference of the computation. I mean, already Kazan-Lustig polynomials are not that easy. If you want to know all the Kazan-Lustig polynomials necessary to compute something for like SL10, you're out of luck. I mean, it's already beyond, the computations we can make. There's too many alcoves below the top restricted alcove to make this feasible. But then again, every computation breaks down at some point if you stick big enough stuff in it. So being real. I should say too, in terms of character formulas, we are in a non-semi-simple setting. So the character of a module far from tells you everything about it. And so you get a lot more information out of Kazan-Lustig and p-Kazan-Lustig polynomials than just the character. So to be fair, I don't want to be like an infomercial. I'm trying to hawk my product by showing you the product you've been using is like inferior, like somebody's vacuuming and their back is breaking. It's like they're just vacuuming. But anyway, these things are computing much more information than just characters. And so that needs to be pointed out. But okay. So I kind of, I'll tell you why I was motivated to think about these. So what are Steinberg quotients? Well, you got to start with the Steinberg module. The Steinberg module is the simple module of p-restricted highest weight. It's the biggest p-restricted highest weight you can have. It's got p-1 in every entry, and that's the cap for the p-restricted weights. That simple module is simultaneously a standard and a co-standard module. It's also a tilting module. So it's simple, it's tilting, it's every kind of module. Basically, we have a special definition for. I didn't even define the G1 is the Frobenius kernel of G. And over the Frobenius kernel, this is the largest of the simple G1 modules. On the other hand, it's projective and injective over G1 is the smallest of those. No, not raising it. And it's got a very interesting role. So the Steinberg module seems to control a whole lot in the category of G modules. One interesting feature about it is it facilitates an embedding of the entire category of G modules into itself, which is sort of a strange thing. So if I take a G module M I Frobenius twist it, and I tensor it with the Steinberg module. That assignment takes the whole category of G modules and stuffs it inside itself with like an isomorphic copy, an equivalent copy. So inside the category of G modules, you have this piece which is equivalent to the whole, and it comes in via the Steinberg. Okay, so here was the idea with Steinberg quotients. So with Dan and Chris and Cornelius, we've thought a lot about tilting modules whose highest weights are the Steinberg weight plus something dominant. And what's nice about tilting modules is we know exactly when they're projective and injective over the first Frobenius kernel is exactly when their highest weight is in this region. So what is useful about being projective and injective over G1 is then that automatically means you have a filtration by what we call baby Verma modules, which really are like Verma modules. You've just cut off p powers of the roots. And so now it's got a special filtration over G1 or even over G1T if you tack a torus onto this, but it's got a filtration over G by standards and co-standards. So it's got two very special filtrations when it's a tilting module having a weight here. And okay, if you can compute all the characters of tilting modules of this form, I should, you've actually computed the characters of all tilting modules. So this is not a reduction to the problem to consider the tilting modules of this form. And sorry, a reduction to the problem of computing tilting characters. So the Riesch-Williamson formula will give you tilting characters for all dominant weights. Now here we're only taking a subset of the dominant weights. We're translating the dominant region by the Steinberg weight. But in fact, this is as hard as the original problem because inside the tilting modules of this form, if you take the highest weight Steinberg weight plus p times something dominant, then it's isomorphic to that by that embedding. And so if you could compute the character of this, then you'd be able to compute the character of that, which is the same. You would know the character of T lambda. So it's not reducing the problem at all. It's just repackaging it. Okay, that's just full disclosure. So, all right, I already said this. Because it's projective, it has a baby Verma filtration. So baby Verma modules all are of the same size. They have the same dimension. And their characters are like translations of the character of the Steinberg character. So what happens is if you have a baby Verma filtration over G1T, then that module actually can be divided by the character of the Steinberg character. And so what you'll get is what we call the Steinberg quotient. So I take the character of this tilting module, I divide out by that, and I get an element that's in the W invariance of Z of X. Okay, so it's just another way to keep track of baby Verma factors. And I should say that this over G1T, and this was motivated by a different paper by Riesch-Williamson called a simple character formula, where they show under the condition P is bigger than or equal to 2H minus 2 a way to get the baby Verma factors for projective indecomposable G1T modules using, there's a periodic p-causal looping polynomial.
Sorry.
Yeah.
So what's the D for the balance of H minus 2?
That was for lifting of, at the time we didn't have the 2H minus 4.
So now it's okay.
Now our bound would, yeah.
New world record.
What's that?
A new world record.
That's right. Now, the advantage of Steinberg quotients, the reason I like thinking about them this way is that you've got elements in the W invariance of ZX. You've got these formal characters. And I think what is maybe new is the work on Steinberg quotients. Basically, the arguments pass from the baby Verma filtrations to to the filtrations by standard and co-standard modules over G. There's some kind of an interplay between these two things that you can sort of facilitate by keeping track of it the way we do. So all you're doing is you're taking the character of a tilting module like this, you're dividing by the Steinberg character. All right, let me not run out of time. Okay, so, all right. I shared this slide at Dan's conference, but again, this is sort of a silly reason to see that I think these are interesting. So if you just inserted P's into Weyl's formula, if you just P dilated rho, then what you would get is that character would just equal this. And this thing right here is not even an element in here. This does not divide the top unless that weight lambda is p times the dominant weight. But here's the thing. In characteristic 0, the simple modules are the tilting modules. So you could revisionist history say that Weyl had come up with a tilting character formula back in 1936 because the tilting modules are the simple modules. They're all the same thing. And so if you just replaced this expression by the tilting module that way over the tilting module that way, you get the Steinberg quotient. So again, that's sort of corny. I wouldn't build a research program around something like that, but it's just kind of, I thought it was a funny little thing to observe. Okay, so here's the deal. These Steinberg quotients, they, well, what are they? They're orbit sums of weights with non-negative coefficients. And the question is which orbit sums are appearing? And so you figure out the coefficients of these orbit sums that appear. So two things that are immediate. One is that the largest orbit that can appear appears once. So S lambda occurs with multiplicity 1. That's what this is saying. And then the second thing follows from the linkage principle, which is a known fact about G modules and G1T modules, that if S mu appears, then that means you've got a baby Verma factor of the size p minus 1 rho plus mu. And the only way that can occur is if that is linked to the top weight. And that's the same as actually this condition right here, that mu minus rho is linked to lambda minus rho. Now this relation comes from the dot action of WA. You just take these affine walls and you reflect around them. But now the dot action just moved everything from acting with 0 as the base point to negative rho. So to say that this is linked to that, you could just as well say mu is somehow linked to lambda, but forget about the dot action. Just do the regular action of the affine Weyl group. So don't do the dot action. Like we just drop those weights and just say that S mu appears with positive multiplicity if mu is like upward linked to lambda, but don't shift the walls. Just stay with the original, the basic action of WA, which is rarely considered. Okay. So the first theorem on this basically says that these orbit multiplicities occur in a non-decreasing fashion. As you, like, if mu minus rho up arrows to mu prime minus rho, then the multiplicity that the orbit for S mu appears is greater than or equal to the multiplicity S mu prime appears. So if I think about my orbit sums, as I go in, they can't get smaller in their multiplicity, which is what was true with orbit sums in Weyl characters. And the ideas of this proof come from the papers listed here, a paper by Weyl. Really, this is the main idea within this paper here. Doty and Sullivan sort of more clearly explain this idea. And then there's a very nice proof, Donkin's proof of the Weyl character formula, which the idea is also borrowed from. Let me try to quickly say what's going on. I want to get to the geometry stuff. Actually, Tekken, let me just ask you, what time does the speaker actually finish?
I mean, if you go 50, 55 minutes, that's fine. So last 5 minutes or 10 minutes. Yeah,
okay, so let me speed up slightly then. Okay, I'm gonna go ahead and bypass the idea of the proof. But it relies on these ingredients. Brouwer's formula, something about yeah, let me bypass that so I can say the stuff at the end I want to say. I can always back up to this if there's time. Okay, so combinatorially, there's a lot of interesting questions about these characters. If you go to the quantum group, then the representation theory of a quantum group at a pth root of 1 looks and smells like the representation theory for G. It's just a little bit different, but they're sort of like an analogous version of everything over there. Steinberg module, tilting module, so on and so forth. You could define quantum Steinberg quotients. And by a known relationship between algebraic tilting modules and quantum tilting modules, we know that these guys are like lower bounds for the T lambda. So they're interesting. And they can actually be computed when P is bigger than H because the multiplicities can be read off from Lustig's conjecture. And this is a reduction in the quantum setting. If you're computing Steinberg quotients for tilting modules, this is a strictly smaller problem than finding the characters of all tilting modules. Because in the quantum setting, what happens is the tilting module's highest weight is Steinberg plus p times lambda is isomorphic to the Steinberg, the quantum Steinberg tensor, the Frobenius twist of a simple module for the classic group. The quantum Frobenius does not land back in the category, or land back at the quantum group, it lands at the classical enveloping algebra. And so these characters, this bit, we know completely what it is. So this is actually a reduction.
I have a question.
Yeah.
Why do you need the balance to be bigger than A?
That was because of a faulty understanding on my part that Lustig's conjecture only held at that point, but I guess it holds in general. You just have to use the parabolic. Yeah. Yeah, I couldn't find that ironed out. You made that comment. I've never gone back and corrected that slide. Yeah.
Yeah, I think it's, you can look at our paper on differentiating the file character form.
Ah, with Chris and Brian?
Yeah.
Okay. Yeah. So, yeah, the quantum group somehow is much better behaved for these kinds of formulas because of this fact right here. Okay. What was interesting was there's a way you can generate a character completely from a character condition. Namely, you can define these characters that have to have a certain kind of multiplication with certain Weyl characters. And these things are super close to being an approximation of the T zeta of the quantum Steinberg quotients. So I want to explore why they're not exactly equal and what you need to tweak to make them that. What the big game I would really love to see is to understand, no, that's not it. I would really love to understand this, why the quantum and the algebraic tilting Steinberg quotients disagree when I have a p-restricted weight in here. So when Lustig's conjecture is true, and assuming that the Donnelly tilting module conjecture holds, these two things have to agree. And so Jordy's counterexamples tell us they disagree awfully for very large primes. And the question is like, why? And I'd love to see a representation theoretic like reason that's just staring us in the face. But that might be asking too much. It might just be the case that there's just certain constants that enter the picture. And certain, I don't know. The reason that Lustig's conjecture fails may not be as satisfying as I'm hoping that it is. It might just be some arithmetic, almost like randomness. That'd be sad. But anyway, okay. I have been guilty of trying to prove things I want to be true, and just, somehow you can't do that. Okay, so here's the conjectural stuff, and let me just hit this in the last little bit. So, all right, so I want to try to connect this to something that I first heard about. I guess it was here when Jordy gave the Cantrell lectures in 2019. I think I made it to his last talk. And so if you take the dual group to G check here, and we'll work with the affine Grassmannian for this dual group, and we're going to work over the complex numbers. I know there's certain applications you would not want to use the complex numbers. You want to use a finite field of a different characteristic. Then where this enters the picture is the geometric Satake equivalence, which says that the category of, I guess, equivariant perverse sheaves over here with coefficients of k is equivalent to the category of G modules. Is this correct? Promote that when P is good, then the indecomposable tilting modules here under this equivalence correspond to what are called parity sheaves on the affine Grassmannian. So something that can be characterized on the left, right? I mean, there's something, if this is an equivalence, that has to be over there, but the question is, what is it? How do you identify it in its native habitat? So that's where we get these parity sheaves are the thing. And so the multiplicative group of non-zero elements in C acts on the power series ring and the Laurent series rings by scalar multiplying the indeterminate Z. And this is, I guess, called loop rotation. And, well, you can restrict that action to the group of the complex groups, a group of p-th roots of unity. So if I restrict to mu p inside of inside CX, I can consider the action of this group on the affine Grassmannian and take the UP fixed points. And so I believe historically this is the correct order, that the first application of, how do you pronounce, is this pronounced Truman or Troyman? Yeah. Truman, okay. Of Truman's work with Smith restriction was by Leslie and Lonergan, where they showed that there's a way that you can make sense of, so this is, contained in the affine Grassmannian, and you can get a functor from the parity sheaves on the affine Grassmannian to parity sheaves on these fixed points. Now it's complicated a little. They have to pass through a lot of different worlds to make these connections, but it's, we're reading that paper a lot. It's a nice paper. And after their work, Reich and Williamson used Smith restriction to get a geometric realization of the linkage principle and prove their tilting conjecture in all characteristics. And they use a different formulation of the Satake category that Laura was a part of, the Iwahori-Whittaker model. So they use a different manifestation here in the Reich-Williamson work. So Leslie and Lonergan did something a little different. But they were able to obtain this functor from parity sheaves here to parity sheaves on this variety of fixed points. And the question is, like, what do parity sheaves on the right correspond to in general? That's my question. I hope it's not a 3-second answer from an expert in the crowd. But anyway, I think this is a reasonable question to ask. So they showed at least part of the answer to this. Okay, so let the affine vowel group act on X via the p-dilated action. We've already talked about that before. But it's going to act via the non-dot action. And so what happens is the affine Grassmannian has, in the normal stratification of it, I mean, the strata are indexed by dominant weights for G, for the torus for G. This is the dual group. And the fixed points have the same strata, but the connected components, the closure of a given strata is no longer all the weights that are less than or equal to it. It's the weights that are like linked under the affine vowel group action. So that up arrow relation earlier, but with the non-dot action. So this thing breaks up into pieces that like match the kinds of orbits that appear in Steinberg quotients. Okay, now there's one piece inside of here that's isomorphic to the original thing. Namely, you take what's called the thin affine Grassmannian, and it's just you take the indeterminate z and replace it by z to the p. This thing is fixed when mu p acts on the parameter z, and it's isomorphic to the whole thing. And so what Leslie and Lonergan did is they obtained, they took their Smith restriction, not sure what I've written there. That doesn't look right at all. Oh, no, I'm sorry. Yeah, they restricted to this piece right here. Yeah, that was the bit in the fixed points. They took one piece that was isomorphic to the whole, and they said using that isomorphism, that this piece is isomorphic to the big piece, they obtained a functor from parity sheaves on the affine Grassmannian to parity sheaves on the affine Grassmannian. And they said, like, what is this functor? And they showed that it corresponded with a geometric realization of a functor that we've played with, some, Dan and I, the Frobenius contraction functor, which has been studied by Gross and Kaneda. And what is this functor? Well, the Frobenius contraction functor is kind of like this. If I take a module that's Frobenius twisted, I can untwist it to a regular G module. The Frobenius contraction is a functor that you can apply to any module, twisted or not. It will untwist the ones that are twisted, but it'll give you something interesting even for a non-twisted module. Here's how you can parse what it does. The Frobenius contraction takes a module M for G, tensors it with the Steinberg module. That's an exact functor because you're tensoring over the field. Then you take Hom, G1, Steinberg into that. Steinberg is projective and injective over G1. That's an exact functor. And then what you're going to get is a module that's trivial over the Frobenius kernel. So it's a twisted thing, and you're going to untwist it at the end. That untwisting is sort of like, in their scheme, it's when you recognize that there's a piece that's isomorphic to the whole, and it's that isomorphism at the end that's sort of what this is doing. So here's the deal. If I take a tilting module and I tensor with the Steinberg module, it breaks up as a bunch of tilting modules that are projective over G1. So it looks like this. And you can group the factors on the right into blocks. I mean, there's going to be all these individual factors. Some of them congregate into blocks, and they stay separate, but all right, forget that comment. That's not helpful. Okay. So the character of the tilting module is the sum of the Steinberg quotients on the right. So if I quotient out the Steinberg character on the left, I'm just left with T lambda. If I quotient out on the right, I'm just left with these little t sigma i's. What happens is when they haul the Steinberg module into here, they're picking out all the factors in that decomposition that are in the G1 Steinberg block. That would be all the ones that look like p minus 1 rho plus a weight that's p times something dominant. So these all look like Steinberg tensor, a twist of a tilting module. So when you haul this thing in, it's picking out a portion of those. And as a T module, what you get is if you take T lambda and you filter it through this, you get a direct sum of all the P weight spaces. Okay. So on the thin piece, this will be the last thing I say. On the thin piece of the affine Grassmannian, the parity sheaves correspond then to the Steinberg quotients. Like if you took a parity object in the original thing and you filtered it through, you get a Steinberg quotient. My question is, can this be expected to hold on the other pieces? I think so, unless somebody's going to burst my bubble. I shouldn't look at anybody in particular. Anyway, that's the last question, but I tend to think there's a strong connection here between these two. And I don't think anybody has an answer for what the Leslie and Lonergan parity sheaves correspond to on the other pieces of the fixed points. Anyway, I better end there because I'm out of time. Thank you. Oh, Nate.
You have this, I mean, this whole sort of relies on, you can divide out the Steinberg character. Is there any hope of there actually being a sort of, I don't know, a reasonable, natural, actual module that is the sort of, that realizes this character?
Yes, like no. So you may know. Right, so these characters are very much formal characters that will not correspond. Like these Steinberg quotients, like what's left, because of the way the orbits appear in this alcove. I'm not explaining anything well, but anyway, yeah, no, these will not correspond to characters of actual modules. They very much are formal things.
But I mean, can they, like, okay, maybe not actual modules, but maybe some, like, you know, complexer modules? Like, is there,
I don't know. I mean, my hope is what would really be a winner is if the parity sheaves on the fixed points affine Grassmannian, I don't even know if this makes sense. Like had the character, I don't even know how you'd say that this, well, anyway, I shouldn't keep looking at promote as if you wrote a book on this. But the point is, yeah, that's a very good question. Like I'm trying to figure out like what's something that makes this more natural and functorial than simply like you've just factored something out and it's completely at the character level and we can't connect it. I think that's what you're asking, yeah. Yeah, I know, it's a very good question. It certainly can't be a module, but what exactly it could be, at the moment, I'm hoping that this would be a really awesome connection. And so maybe it's pie in the sky, but I think it might, yeah.
So I don't have anything really knowledgeable to say, but yes, I guess that the other components of the fixed point set, they're not necessarily copies of the affine Grassmannian, but they could be the affine flag variety or something in between the affine flag variety or the affine Grassmannian. And I think like, you know, you're like this piece that you wrote down, you're obtaining things that I mean, this thing you explained about like tensoring the Steinberg module, it's supposed to be like the tilting modules in the block of the in the block of the Steinberg character, and parity sheaves on the other components should have to do with tilting modules in other blocks.
They should?
Yeah.
That would be
and I think
really good.
I mean, this is something that I don't know the like as you mentioned, like the Rieschoum's version of Smith localization is not exactly the same as Leslie Lonergan, and so like do you know if they agree on this zeroth piece? Like,
no, that's what's so confusing. Like the Reich-Williamson, they really have to use the Iwahori-Whittaker. Like their argument depends on that, which was cool because I remember seeing Laura talk about this at some point, and I not really understanding like what, like why do we, I barely understood what the first equivalence was. Why do we need the second one? Well, it really, like their work had to use that, and fundamentally you get something different. I think their Smith restriction is like a fully faithful thing, whereas the Frobenius contraction is absolutely not. You can have tilting modules with no morphisms, and then you do Frobenius contraction, there's morphisms here. So it's like fundamentally a different deal. But what you just said about on the partial flag varieties and things, those other pieces,
I think like
that would be good.
The target category of like on the other components, the target category should look like tilting modules in the other blocks, but I think I don't.
That's what I'm hoping. I mean, somehow the character has to like the parity. Well, I have a few technical questions I'd like to ask you later. I won't bore everybody else with, but that's helpful. Yeah. It's just a turnkey paper here. All you have to do for mode is prove one thing to me, and we got a paper. And I'll be back in 3 months. And I'll...
Other questions? If not, let's thank this speaker again.
Well, we're going to have 15 minutes break, and then we start at 5:15.
Oh.
Giving a board talk.
I'm getting a board talk, yeah.
I didn't even really use my picture, but I didn't. I was running out of time.
Oh yeah, I mean, I love to use my Oh yeah, I'm not doing that.
Very good. They're not here. Right. Second, really hard. But they.